Okay, students, today we'll start with the next topic. In fact, we have left with 3 intermediates now, out of which this what we discuss is carbines first. So start writing with me. So these 3 are very theoretical, very less used in JEE. Nevertheless, we'll just go through these terms carefully. Firstly, let us see what is a carbene. Well, carbene is a neutral species. Keep writing with me. It is a neutral bivalent species with 6 electrons present, which means it is octet incomplete. When you have 6 electrons, it is also called as sextet. So sextet electrons, that is called as carbene. And this carbene are of 2 kinds. There are 2 types of carbenes. One is called the singlet carbene, and the other one is triplet carbene, singlet and triplet carbene. Let us try to understand the difference between these two now. When it comes to singlet, by structure, if you observe, it would have CH2 with an empty orbital, and other orbital will have a pair of electrons. While if you see on the triplet side, I have CH2 with 2 radicals, which means 2 unpaired electrons. So it would have 2 orbitals, both will have 1 unpaired electrons. Everyone, I hope you got the point. Which means, what is a hybridization here? This carbon would involve hybridization into these 2 hydrogens as well as this lone pair, which makes it an sp2 hybridized orbital like this. Empty orbital, we have hydrogen, and here we will have a pair of electrons. So this would be an sp2 hybridized orbital. While on the other hand, if you observe this carbon here, it would be almost linear because it would try to keep only sp hybridization. This is almost perpendicular. So we have hydrogen, and both of them are p orbitals only. So 1 electron here and 1 electron here. This is the triplet kind. While here we have a diplet kind, which means there is 1 pair of electron here. So the bond angle that it will sweep is around 105 degrees. And you can see there is 1 completely empty orbital present in here. Okay, so this is a completely empty orbital. While here, both the p orbitals have at least 1 electron each. The bond angle which this sweeps here is around 135 degrees, and the hybridization which it makes is sp hybridized. So it is sp hybridized with a bond angle of around 135. Write these 2 differences, everybody. Make a column, one of singlet, one of triplet. Okay. Now see the next point. That is, how is its spin multiplicity? Spin multiplicity. Spin multiplicity as in how many number of unpaired electrons are present in the particular molecule. Based on that, if you remember the Hund's rule, we can define how much is the spin factor that will contribute towards the overall spin of the molecule. So you can write this as 2s plus 1. Remember this as a formula. Spin multiplicity is 2s plus 1, where s is the total number of unpaired electrons. So 2 into, when it comes to singlet, there are no unpaired electrons. It's a pair electron. So 2 into 0 plus 1. So the spin multiplicity is only 1. That's why the name given is singlet. That's why it is termed as singlet. While on the other hand, if you see the spin multiplicity here, that is equal to 2s plus 1, And you could see there are two unpaired electrons present in it. So the total spin here is 2 into 1, because every unpaired electron contribute a spin of half. So you can see half plus half, that will contribute to a spin of 1. So spin multiplicity will be 2 into 1 plus 1. So that is 3. That's why it is called as a triplet carbene. So the terminology comes from how much amount of the spin multiplicity is present. If you check out stability wise, singlet is always less stable than triplet. In case of stability, we can say that singlet is always less stable than triplet. Well, why does that happen? You can see triplet carbene is more stable than singlet due to exchange energy. If you just recall electronic configuration from structure of atom, okay, why the unpaired electrons, in the degenerate orbitals were always given one electron each like this, instead of directly clubbing them in one orbital, this way as a pair. We will always go for this type of configuration. The reason for is the number of exchanges that it can make. So there are 3 exchanges possible here. More the number of exchanges, which means more is the movement of electron around the nucleus, and that decreases the electronic repulsions and increases the stability. So in short, Hund's rule is all about trying to decrease the electronic repulsions and making them more stable. So keeping more unpaired electrons in degenerate orbitals will relieve the repulsions. So basically here we meant that CH2, one with an empty orbital and this way, which is a singlet form, is less stable than that of CH2 with 2 single electrons. Let us see the next point. In case if the same singlets are present with halides, we call it as dihallocarbenes. So in case of dihallocarbenes, singlets are more stable. Now you see what is happening here. Suppose if at all we take the singlet form, in singlet form we know that we have a lone pair here, and 2 chlorines present here. For example, I'm taking chlorine as an example. Suppose if you have this lone pair on chlorine, you can see that there is an empty p orbital. 2p orbital is empty here, and in the 3p orbital we have a pair of electrons and they are parallel to each other. So definitely we can expect a pi bond to form here, which is through back bonding. Got it? So the molecule will become stabilized by the back bonding from the lone pair present in 3p orbitals. So from 3p of chlorine, a back bonding can be established, because of which it will become more stable, which is not possible when you have a triplet carbene. Because in triplet carbene, we will see the molecule is something like this here, but both of them have at least 1 electron, so the back bond is completely avoided here. So no back bonding will take place here. Hence, stability wise, if you check out for halides where there is a lone pair present on them, the singlet would become more stable. So within the halides, if we compare, suppose if we are comparing with fluorine, chlorine and so on, so definitely fluorine would be the best, because it would give an back bonding of overlapping 2p 2p kind, as compared to that of CCl2, where it will give 2p 3p kind, where it gives Br2 with 2p 4p kind, and Ci2 which is 2p 5p kind. So this is a type of overlapping and stability order. Another case where you will see the singlet being more stable. Suppose if at all I take a tropylium carbocation, tropylium molecule like this. With, imagine this carbon is, singlet type like this. There is a singlet carbon, and the same molecule, it may be in a triplet form. Triplet form as in it has one electron here and one electron here, correct? If there is an empty orbital, definitely these 3 pi electrons will keep completing the ring current and make it aromatic, which is not the case in triplet form. So hence, to attain the aromaticity, now the singlet form would be more stable. Got it? So this gets this 6 pi electron loop, which will make it aromatic. If you recall tropylium carbocation beta, tropylium carbocation was this way, right? With an empty orbital, right? And that used to give resonance because there is an empty orbital. So this pi used to shift, and that way the ring current used to establish. If there is an empty orbital, definitely the delocalization will take place. How can we generate empty orbital? If it is a carbon molecule, should you put singlet form or a triplet form? To generate carbon molecule, what we can do alpha elimination, which is also known as 1,1 elimination. For instance, if I take chloroform, Cl, Cl, Cl and H, and when you treat that with a strong base like ATO minus K plus, this ATO minus is a very strong base. It will extract the proton from here and it will convert into ETOH. So ETOH plus Cl, C, Cl, Cl, Cl with minus. And this will become a conjugate base. Now this conjugate base is unstable form. What will it do? It will immediately dissociate into, it will remove this chlorine, will take away electrons and come out as Cl minus and generate CCl2 plus Cl minus. So what happened? Elimination happened from the same carbon. No? Hydrogen is also going from the alpha carbon. Chlorine is also going from the alpha carbon. So that's why it is called alpha elimination. So H as well as Cl both have eliminated from the alpha position only to generate this type of an carbene molecule. This is one way of generating carbene. This is by photolysis. Yesterday we have seen photolysis or pyrolysis, how we can see radicals are generated. In this case, if we have diisoalkane, then we can see the photolysis can happen. For instance, if we have R, CH, N, triple bond N plus. N2 is a highly stable molecule. So even if you provide a small amount of energy or light, it would immediately come out as N2. So when you have RCH minus connected to N2 here, the minute you heat it or provide light, it would immediately break to form RCH like this plus N2. Now this would form what? A singlet or a triplet carbene. And most of the time, since triplet is more stable, you will have triplet form formed more than the singlet form. And N2 gas will come out of it. This is second way of generating. Third way, we can do the photolysis of aziridine. Photolysis of aziridine. That If you take R, CH, and N is connected this way with a double bond here, on heating or on photolysis, these two bonds will break and it will make an carbene molecule plus N2 gas. These are the ways by which we usually prepare carbene. Check out once again, everyone, make a note. This lone pair can exist in two forms, na beta. Either it can have an empty orbital with H and a lone pair like this, which is a singlet form, or it can have in a triplet form like this. Correct? Usually it will prefer triplet because that is more stable form. Carbene can be generated through any of these three ways, beta, where we need to get carbon to have only 6 electrons on it. Okay. One is it is connected to R, other it is connected to H. Now there is one lone pair which was present on it that might distribute in this form or this form. That's it. Okay. Now how it is generated depends upon what molecule it is connected to. If it is connected to something like a very stable molecule N2, N2 is a highly stable molecule. Its bond dissociation enthalpy are 910 kilocalories, which is huge. So it would always try to exist as N2 rather than connecting with some any alkyl group. The minute you provide some amount of heat, it immediately comes out as N2. So that carbon, although it has an octet incomplete form, there is no other alternative but to be existing in a singlet or a triplet form. Now see, when it comes to fate of carbene, what type of a reaction this carbene will take place? The first type is dimerization, because definitely it has a 6 electrons. It is highly unstable form. So it would immediately try to dimerize. So RCH plus CHR. Whether it is a singlet or a triplet form, both of them will dimerize to form RCH double bond CHR. This way it will undergo dimerization and gets a double bond between that carbons. Second, it get addition to pi bonds. If there are any pi bonds, it get added onto that pi bond. For example, if you have CH2 double bond CH2 plus CH2 this way, then it get added up to give CH2, CH2 and CH2. In fact, this is the way you can prepare cyclopropane. Okay. In case if you have CCl2, then it would become dichlorocyclopropene. In case if you have a triple bond, C triple bond CH plus 2 moles of CCl, CH2 for instance. If you have CH2, I'm taking 2 moles of it. So, one, it get connected with the above carbon like this, CH2, and one below. Both pi bonds get added up. So, in short, the structure would look like this. See, two other cases where carbenes are formed. Just make a note of it. If you have space, just write it here itself. I've written 3. I'll have 2 more cases. If you don't have a space there, just make it a note up there. In case if you have CH3, CH double bond C double bond O. This is a keto form with an ene. That's why it is called ketene. Ketenes also, in case if we, make photolysis or pyrolysis, it would give CH3, CH plus CO. Similar to what you are saying in aziridine or diazo molecules, here also the same thing would happen. Check out how the mechanism is. Basically, we have CH3, CH double bond CO. On heating, the lone pair present on oxygen would immediately try to close it as a triple bond, and minus charge would come on here. So we'll have CH3, CH minus with C, triple bond O and plus. And the minute we heat it further, this will dissociate and it will take CH3, CH pair plus C triple bond O minus and plus. This way it will split. Point is clear? Here it is an heterolytic cleavage. C minus will take away the electron and become CO gas. Another way we can generate is if we get an aromatic form. In case if we have two biphenyls connected this way with another carbon here, and on heating this particular carbon which is present, okay, it will break completely. It will break here, it will break here and makes a double bond formation and become phenanthracene like this, and a double bond will come here, okay, and converts that to CH2. So carbene is produced that way. So these are few ways by which you can prepare carbenes. Nitrines are not directly there in JEE syllabus. It will come only in one case in the entire organic chemistry. Only at one particular case you will come across nitrine. Right? Other than that, there is no special mention anywhere of nitrine. We'll keep it short for nitrine. See, just like how we had carbene, here also nitrine will have Rn with two lone pairs. This is also a sextet, so I can say that this will also have 6 electron, that is sextet configuration. Okay, and this will also exist in both singlet form as well as triplet form. Let me write the structure like Rn, if it is an empty orbital with two other orbitals this way. So you can see it is an sp2 hybridized nitrine with an empty orbital. So we call it as singlet. In case if we have Rn with one electron each, all of this, one electron in this orbital, one electron in this orbital, and one is hybridized this way. So you can see it is an sp hybridized now. This is an sp hybridized with one electron in maybe some px and one electron in py, and pz has been participating in hybridization. So here the hybridization for nitrogen is sp, and this is a triplet form. So just like carbenes, we have singlet nitrines and singlet triplet nitrines. How do we generate here? Generation is by photolysis. Most of the time it is by photolysis or by pyrolysis. Pyrolysis is also used as thermolysis, okay? So basically it's all about using heat of azides. For example, if you have azides, azide is Rn3. If you recall hydrozoic acid from inorganic, it would be like this, double bond N with H with plus and minus. This is hydrozoic acid. And if you remove this hydrogen out, correct? In case if you remove this hydrogen out, we get N minus, double bond N plus, and double bond N minus. This is azide. This is azide ion. A hydrozoic acid will always give an azide conjugate base. It will convert into Rn plus N2. And this N will have two lone pairs. So you can see it has only 6 electron system. So Rn double bond N plus with minus charge here and a lone pair here. This is how azide was connected to alkyl group. So the lone pair will support here as a triple bond, and single bond, this pi bond will shift onto nitrogen, giving to form Rn with two lone pairs, single bond, N, triple bond N plus charge. Okay, and this is getting minus charge. This is how it would. And on heating, there will be an heterolytic cleavage here, forming this as N with two lone pairs and N2. So that's how you will see nitrene is formed. Let's see what is the fate of nitrene. It can dimerize just like carbenes. In fact, any 6 electron species will try to dimerize. This, taking 2 moles of it, will dimerize to form R and double bond N and R. This is the formation you will see. It can get added up, can add to pi bonds, just like carbene. So in case if we have CH2, double bond CH2 plus Rn, it will get added up to this and becomes a hetero ring like this with a lone pair on it. So this is the fate of nitrate. Okay. One very important part in benzene is all carbons are sp2 hybridized. All carbons are sp2 hybridized. It would have 6 pi electron closed loop. When you have 6 pi electrons, which means it is following 4n plus 2 rule, which shows it is aromatic. So benzene is aromatic, and along with that, it would have 3 p pi bonds, 3 p pi irregular bonds, okay, and 1 sp2 pi bond. So this is one of those instances where there is an hybridized orbital making a pi bond, okay, and because their distance is not exactly parallel and they are slightly far away from each other, this will be relatively weak bond. This is a weak bond. How do we need to represent it? Normally when it comes to benzene, we show it as a circle here, and outside if we show a bond here, that is called a benzene bond. If you see the orbital wise, it is like this. This is a canonical, and this carbon has one sp2 hybridized which has only one electron present in it. So one electron here and one electron here, both of them will make a pi bond between them. So this pi bond is between sp2 and sp2, so that's why it is called sp2 pi bond formation. Just like benzene will also have two canonical forms. You can see one benzene is this way, and the other benzene formation is that this pi bond is here only, but I'll make the other Kekulé structures like this. So these two are benzene forms. If we check out the stability wise, suppose if I call this as 1 and 2, 1 is more stable than 2. Okay, and these two are canonical forms. Now let us see how to generate benzene. In which cases we'll usually see benzene is formed. Let's try to understand that. First case is dehydrohalogenation. Dehydrohalogenation of aryl halides. If any halide is directly connected to benzene, it is called aryl halide. Suppose this is benzene, to which if halide like chlorine is directly connected, we call it as aryl halide. And we know there is hydrogen here. When you treat that with a very strong base like NaNH2, NaNH2 is called soda-amide or sodamide. Sodamide is a very strong base. So what will it do? It will make a benzyne formation like this. Let me show you the mechanism. So this benzene which is present, NH2 minus being a strong base. I told you yesterday, when you say something as a base, it is always a proton extractor, which means it will try to extract the proton from the opposite species. If it is used as a term nucleophile, it will connect it to the carbon. Okay, so NH2 will extract proton from here, so the negative charge will be generated on benzene. So we will get a group like this with negative charge here with chlorine and NH3. And this species, now this minus charge which has formed, will try to close it as a triple bond here and chlorine will come out. And that's how we'll see a benzene is formed. This way a benzene is formed plus Cl minus. So dehydrohalogenation of aryl halides will generate the benzene form. Second way to generate benzene is by using 1,2-dihalobenzene. In case if you have any 1,2-dihalobenzene, preferably chlorine or bromine. Fluorine and iodine does not give a great result in this. So chlorine and bromine, in case if they are present on 1 and 2 position of benzene, then how do we generate? Let's see that. If you see benzene with chlorine here and chlorine here, you react that with metals like magnesium or zinc. Both these metals are electron donating species. They will donate electrons and make bonds with this chlorine. So we would have generation of benzene form here plus MgCl2 or ZnCl2 formation. Think this way, that magnesium or zinc, I'll take it one case, it is giving electrons. Electrons, as they approach towards benzene, we have chlorine and chlorine here. So when two electrons approach here, so imagine as if these electrons, are attacking from the top of this carbon-carbon double bond, and which generates that both the chlorines will remove out and we'll get this with 2Cl minus coming out. Okay, so you can think this way, that these two electrons which are present here are trying to donate one electron onto this side and one electron here. That, see the next way, this is by electrolysis of phthalates. Remember phthalic acid? So on benzene, if we have COOH, we call it as benzoic acid. If you have 2 COOH, we call it as phthalic acid. And in case if they are in a salt form, we call it as phthalates. So phthalates also will convert into benzene form by coming out as carbon dioxide, CO2. 2 moles of carbon dioxide will come. Okay. If you remember, the other day we discussed that what happens in electrolysis, coal-based electrolysis. Coal-based electrolysis is done wherever there is a carboxylate, that is CO minus, they will give electrons first. On electrolysis, they will give CO minus plus 2 electrons. And CO minus species are unstable. They will come out as carbon dioxide, leaving behind the radical. So one radical here and one radical here plus 2 CO2. And these radicals will terminate to form benzene. So if you check out the mechanism, this is how exactly it happens. Fourth way to prepare the benzene is by heating diisobenzoates. For example, if you have COO minus, this is an 8 salt, and imagine N2 plus is present on the other side, which is diiso group. N2 is an highly unstable species because N2 on a molecule is an unstable species as it can easily convert into N2 on heating. So on heating, immediately this bond breaks. And as soon as it breaks, you can see what we can see here. We already have these pi bonds. We have C double bond O, O minus, and this bond is breaking here as N2. So N2 means it will take away electrons. As it takes away electrons, this CO2 will also come out, and this sigma bond will support as a pi bond here. And these electrons will, the lone pair present on oxygen will try to convert it as CO2. So we will have CO2 plus N2, and the remaining molecule which is present will now takes the form of benzene. This is how the benzene is formed in this. The question that could be asked is how many gases are formed in here. So you can see 2 moles of gases would come when you heat diisobenzoates. The radical formed here should also support a radical here. Now here there will be only carbocation formed. If both sides radical are formed, then that will be happening. Like here there is a radical that will be formed, but here there will be positive charge coming, na beta. So electrolysis is not going to help. Okay. Next, see what would happen to the fate of benzenes. See, benzenes are also highly unstable because there is this, sp2 pi bond which is formed, but that is not very stable pi bond. Got it? So unless there is anything to react, got it? If benzene alone is formed as intermediate, and no other species to react, then benzene undergoes dimerization. It will undergo dimerization. Okay. So we can see that we can have benzene here, and the other benzene this way. If at all I put it on both sides, adding both of them, we can get a dimer form. So this type of a dimer is formed. But see the issue with the dimer. The issue with this dimer is this ring is aromatic, but the ring which has formed at the center is anti-aromatic. So if at all I write the canonical, let me take this as canonical 1 and the other form of canonical. After forming, it can have 2 types of canonicals. This is the other type of canonical. Okay. So if you consider these 2 canonicals of dimerized form of benzene, then this canonical is not showing that anti-aromatic nature, because this side there is aromatic form, this side there is aromatic form. But since the pi bonds are not completely coming into this ring, it is not showing that anti-aromatic form. Got it? So I can say if you check out the stability wise, it will be 2 greater than 1. Okay. But still, any form of a dimer that is formed, whether it is the first one or the second one, they are not very stable. Got it? And these dimers are not stable. So depending upon the quantity of benzene, if benzene quantity is quite good enough, they would prefer to form trimer rather than dimer. So if at all I take 3 moles of it, they will try to form a trimerized form. So if you see the trimerized form, how it forms, see, it is forming trimer here, this way, and this way. Now you can see 3 moles have formed a trimer. So this trimerization will help it to achieve more stable species. Got it? Why? Now if you consider this ring, this is all 4 rings are aromatic. This is aromatic, this is aromatic, this is aromatic, and the center ring which has formed is also an aromatic form. All rings are aromatic. So if you were asked a question like between dimerization and trimerization, which will be more preferred in case of benzene, then that will be trimer form. But dimer form is also achieved, got it, with this type of canonical being more stable. And this molecule is known as biphenyline. Biphenyline. Biphenyline, which will become a solid form, solid state. Correct. At the same time, this triphenyline is also formed, that is also exists in a solid form. Given the depending upon the quantity of compound given, it could have dimer form also and trimer form also. Preferred would be always trimer form. No, this CO2 is going, so negative charge is created here. N2 is going, so positive charge is created here. So positive negative is making a double bond. So these are the specific intermediates we will come across all the chapters. Henceforth, when we start mechanism, you will come across carbocations, carbanions, radicals, then carbenes, nitrines very rarely, then benzene. These are the forms you will get. One more form which you will get is radical ion. Radical ion. Only in one reaction you will get this, where you will have a radical form like this. There is a radical form on carbon, and maybe oxygen or any group that is connected will have a negative charge on it. So these kind of species are called radical ions. Another form where you can get is C double bond C, with this being R and one radical form on carbon here, and the other side we have a lone pair and R. This is also a radical ion. Okay, so you will come across this. These are the radical ion forms. Only the information is needed, that's all. If in case if the exam you come across a term like what is radical ion, these kinds are called radical ions. Now let me recall, we have studied mainly when it comes to electronic effects. Electronic effects, we have studied 3 important kinds. One is inductive, the other one is resonance, and then we studied hyperconjugation. Now all 3 were permanent effects, which means there is no compulsion that there is some change has to bring to the species, some heat has to be given, like that, nothing. If a molecule exists, it might show inductive effect or it might show resonance or hyperconjugation, irrespective of any molecule, any external factor that has to be involved. But there is one effect which is temporary and only happens in multiple bonds. This type of effect is called electromeric effect. While electromeric effect, the first point, it is temporary effect. Temporary effect. Second point, it is usually seen in multiple bonds, which means when you have a double bond or a triple bond. Okay, multiple bonds, double bond or a triple bond. So basically it is defined as a pi electron transfer of a shared pair, pi electron transfer of a shared pair of pi electrons to one of the atom joined by multiple bonds. on demand of attacking reagent. What does this mean? Suppose if we take a double bond here, let's say, imagine an electrophile is approaching. Electrophile will always come with an empty orbital. Okay, so there is an electrophile approaching here. Got it? So now this, what will this pi bond do? This pi bond being a nucleophile, because you remember pi bond is always an electron rich cloud. So this electron rich cloud will try to attack on this electrophile. That is the nature of this electrophile. So before attacking, it will go through a temporary state. See, if this electrophile is far away, nothing will happen. This will be a non-polar existence like this. But the minute this electrophile start approaching towards this species, some changes will happen here. This pi bond will completely shift onto any of the carbons, either left side of the carbon or right side of the carbon. So imagine if it shifts onto the right side of the carbon. So it will get, negative charge here and positive charge here. Then as the electron comes very close to it, then this will attack on it and hence forms a carbocation. So an electrophile gets attached and a carbocation is formed this way. Got it? Now this type of an attack, where in the species what is happening, within the species the pi bond is moving on the carbon itself, correct? So this type of effect is called positive electromeric effect. So this is plus electromeric effect. So positive electromeric effect, as in the pi electrons of multiple bonds are transferred to that atom to which reagent is attached. Another simple way of understanding, see, which is the main chain in this molecule? The main chain is this carbon double bond carbon only. I mean, either the main chain will go like this or the main chain will go like this. But these two carbons will fall on the main chain only. When the electrons distribution happens only on the main chain, it is called plus E effect. So it is called plus electromeric effect or plus E effect. When do we see it as a minus E effect? See, that would happen away from the main chain. Got it? For example, if you have C double bond O, and if you see this is the main chain, like this is how the main chain is. This is a keto group. And originally there is some amount of delta positive and delta negative like this. Delta positive and delta negative. Got it? But there is no permanent shift of this pi bond, right? Now the minute an electrophile approaches here, suppose an electrophile approaches here, the lone pair present on oxygen will try to connect, correct? But before doing that, like I said, temporarily you will see this carbon will get positive charge, oxygen will get negative charge, and electrophile will be approached by this lone pair, and you will get carbon positive charge with oxygen and electrophile forming like this. Now this time, if you see the electronic distribution is away from the main chain, correct? So then we call it as a minus E effect. So in this case, this is a minus E effect. So minus electromeric effect. This honestly, when we do the mechanism, we do not address plus E and minus E. But if you are specifically asked what is plus E and minus E, then we have to show this. But this is not a transition state. Please remember this. While writing the mechanism, we do not use electromeric effect as a transition state. Okay. Suppose, what kind of a questions that could come here? Now suppose if there is a double bond here and an electrophile is approaching. Okay. If at all I write in terms of molecule, it is CH3, CH double bond CH2. So an electrophile is approaching. Originally before, sorry, before approaching any electrophile, see electrophile is far away. This molecule will remain non-polar. Nothing will happen here. Maybe some polarity because of hyperconjugation and all, but between carbon and carbon, there is hardly any charge difference. But the minute the electrophile approach close to it, then the electrons get distributed on any of the carbon. So you can see as the electrophile approaches, we have two different ways by which it can rearrange. One, it can form this way, CH3, CH plus and CH2 minus. This, or the other way is CH3, CH minus and CH2 plus. This is the electronic rearrangement, and both of them are plus C effect only because minus charge is still moving around the principal chain. And as the electrophile gets combined with it now, we will get this as CH3, CH plus and CH2E. This is what is formed. In here we will get CH3, CH electrophile and CH2 plus. Now you will be asked which of these electromeric effect is more effective or major product. When electromeric effect happens, these two are feasible forms. Which is more stable between these two? Check out on the basis of the product form. This carbocation is forming on the secondary position. This carbocation is forming on the primary position. So which is more stable beta? The first route, right? So this path. Everybody understood this? So we'll call it as path A and this one is path B. So the first path is more preferable. Hence, this product what you will get is a major product and this product what you will get is a minor product. This can be asked in exams, like which of them will be forming as a major product and which of them will forming as a minor product. Make a note everybody. This is a transition state. This one is not. This plus minus we do not show. Electrochemical effect we do not show in transition state because it is just a temporary effect. Okay. And it is not very much accounted as a special step, in reaction. There is an electrophile approaching with delta positive. This pi bond is moving and this is getting delta positive. This is the transition state. Have you understood that? I won't show these transitions. Now let us see one important application that comes through resonance. Yes, that is called steric inhibition of resonance. Steric inhibition of resonance, also termed as SIR effect. What it is, see on benzene, okay, imagine there is some group like NO2. This is definitely planar molecule because all of them are sp2 hybridized. It is a planar molecule. Now, if there is one group here and another group here which has quite enough size to give sufficient repulsions here. So if these two molecules would have sufficient repulsions here, then this molecule will try to come away from the plane of these two. Now what would happen? That molecule will try to rotate such a way. Originally if you see the molecule is this way. We have N. On the same plane we have oxygens and resonance is happening here. And this way the molecule has been. Now due to the repulsions from these groups towards oxygen here, this bond will rotate. This bond will rotate such a way. Now we will have nitrogen with this oxygen going inside and this oxygen coming outside. And resonance here is intact. Okay. And these two bulky groups are here. Just to avoid the repulsions between these two, what happened? This bond has rotated to this point. So what happens here if the bond rotates? See, originally what was happening here is that this pi bond which is present, if you check out in this, the pi bond which is present here, everyone check. So this pi bond of nitrogen which is present here was in resonance. I'll show the pi bond this way. Yeah, show this. This pi bond was in resonance with this pi orbital. This way it was in resonance. Correct? Now the minute if you rotate this bond, that pi bond will become almost perpendicular now. This is this way and this orbital is this way. So almost these two have become perpendicular to that orbital. So the resonance between these two will stop. So there won't be any resonance happening between the benzene and the group which is present outside, because both the orbitals will go opposite to each other now. I guess all of you understood this point. And why they had rotated? To avoid the van der Waals repulsions coming from the groups on the ortho position. So to avoid that, it has compromised the resonance happening with benzene. Because of which, now what would happen? The resonance of benzene will be only within the benzene ring. This resonance will all anyway continue, but there won't be any form of resonance happening between these two. Right? So this type of resonance inhibition between the benzene ring and the outside group is called SIR effect, steric inhibition of resonance. I guess this point is clear. Now imagine as an example I give you, if we have NO2 here and there are two bulky groups like iodines. There is one iodine here, one iodine here. So iodines are sufficiently bulky. And then we have one more NO2 group here. Now if I analyze the bond length here X and bond length here as Y, got it? Due to SIR effect, this NO2 will be out of the plane. I mean, this NO2 will be out of the plane of this iodine and iodine. Got it? Because of which the resonance that has to happen between benzene and nitrogen here is prohibited, and here the resonance is still taking place. There is no issue with this. So from here we can say that the bond length between X and Y, if you check out, then X will be greater than Y. Okay, so what is that? Here, let me write down here, I groups will force NO2 to go out of the plane, okay. This makes p orbital of nitrogen perpendicular to benzene ring. Hence resonance. Okay, everybody, I hope you understood that. Let me give a few applications here. Suppose if you were asked, like, I have NMe twice, okay, N and dimethyl amine, aniline. Okay, so this is an aniline form, N and dimethyl aniline. Suppose here the bond length is X. I'll take this as first form, second form. In case if you have NMe twice with two NO2 groups here, NO2 groups are also bulky enough. They're sufficiently bulky here. And let's say this bond length is Y. So tell me which one will have more bond length here? Right, Y greater than X here. Got it? First we'll do simple terms, how the bond length varies. Second example. Suppose if we have to check out the ring density with OH group here, and there is NO2 group here, NO2 here, and NO2 here. Got it? And I'm trying to compare the same with OH with NO2 here, NO2 here, and CN group here. Now, between these two, right? So which one will be more withdrawing, correct? So if you ask, like, you know, here NO2 is there, here CN is there. If I compare NO2 and CN, right, which is more withdrawing group here? 1 and 2. If we consider, the question is between NO2 and CN, which is more electron withdrawing group? Normally, when we say NO2 is always more withdrawing than CN, considering it is showing both -M and -I. But here NO2 will get steric repulsions from both of them, because of which here it only shows -I effect. But cyanide is a linear molecule. Cyanide would be like this, right? C triple bond N. It is linear. So linear molecules does not experience any repulsions from this, you know, bulky ortho groups. So here this will show both -I as well as -M effect. So which is more electron withdrawing, students, here? Correct. So cyanide is more withdrawing than NO2 groups. Clear? So now we need to understand which particular groups will not show SIR effect, which particular groups will show SIR effect. Okay. So groups which does not show, which does not get affected by steric hindrance, those groups are OH, got it, cyanide, fluorine, chlorine. These groups, when you have it at, you know, this bulky positions where ortho, there are a lot of bulky groups, they don't get affected. Their +M, -M, -I, that will continue to happen. But groups which get affected, groups which gets affected by SR, right, that would be all of this, NH2, okay, sorry, NMe2 twice, NHMe, got it, NO2, COOH, SO3H, CHO, OCH3, iodine, bromine, COOR, okay. NH2 won't get affected. I have not written here, sorry, NH2. Okay, I'll show you one example here. This is C. Suppose if you have NH2 here and two bulky groups like NO2 and NO2, got it? And then we have NH2 here, sorry, NH methyl group here, NO2 and NO2. Now this second one experiences SIR effect. And if you see the third one, where you have two methyl groups here, this experiences the maximum, where the resonance is almost cut completely. So this experiences the maximum SIR effect. NH2 here experiences the minimum SIR effect. In fact, we will still say that this resonance is, you know, quite feasible. This resonance, to some extent, here resonance is completely prohibited. Got it? So if you were asked, like, you know, what is the basic nature of this NH2? Because if the lone pair is localized, it will act more basic. If the lone pair is more delocalized, it will act less basic. Okay. So in case if at all we take this as 1, 2 and 3, And if you were asked what is the basic nature of these molecules, which one is more basic nature here? Third one is more basic nature than second one, then first one. And this is due to SIR effect. So suppose you guys understood that. So which case it will get affected, which case will give SIR effect, correct? So you should be able to identify that.